to the cloud. So again, these questions are asking us to do cofactor expansion. In this case, particularly across the third row to compute the determinant of A. All right, and so that's kind of like the big strategy there. It's just kind of deciding what the best approach to take would be. You know, you kind of look at this and say, well, maybe we'll go across row 2 or row 3. It doesn't. Oh, it said row 3. Sorry, highlighted the wrong thing. Row 2 or row 3, and you kind of pick and choose. In this case, you might say, I'll go with row 2 because I got smaller numbers, smaller absolute values. But in this case, it's telling us to go across the third row. But even if it didn't, I might have selected this anyway, just because they're positive. And then if they're positive, I'm going to have to worry about signage less, right? So -1 raised to the, we're in row 3. So we're going to assume 3 plus 1 is my exponent, right, multiplied by the entry in row 3, 1, row 3, column 1, which is 1, multiplied by the determinant of the entries that remain when I eliminate row 3 and column 1. All right, so I'm just going to write it. So 5, -4, 1, -1. So then, kind of looks nice. The next entry is a sum. Let me get a different color here to represent the sum. The sum is going to be related to -1 to the 3 plus 2, row 3, column 2, multiplied by the entry in row 3, column 2, multiplied by the determinant of the 2 by 2 square matrix that remains after I get rid of the row and column that contains the 2. Right? So if I do that, it looks like 1, -4, 0, -1.
Professor, after the -1, you multiply for the row number or the number that's in the row?
The number that's in the position.
In the column. So it's like, is that 2 or?
Yeah. So in the first case, it was the 1.
Oh, you're starting by the third row.
Exactly.
Thank you.
And then the last one is going to, -1 to 3 plus 3, but then it's going to be multiplied by 0. So the whole thing is going to zero out, which is the beauty of selecting something like row 3 or row 2 or row 3. But specifically choosing row 3 is kind of, you sort of finish strong, there's a little bit of benefit to that. In the case of -1 to the 3 plus 1 power, that's kind of nice because any value that's raised to an even power is going to be positive. So that's going to a 1. So it's really just this whole thing is going to culminate in whatever the diagonal down minus the diagonal up is. So -5 minus the -4 plus we're going to have -1 to the 5th power, but more importantly, an odd power is going to give a negative result. So -2, so I'll keep that in mind, multiplied by diagonal down minus diagonal up. So -2 multiplied by really just a -1. And so when we crunch those numbers, clean that up a little bit. So -5 plus 1 plus 4 is going to be a -1, plus 2 is going to be a +1. All right. So we can verify that. If I screwed it up, we're going to find out pretty quickly. Put the values in, 1, 5, -4, 0, 1, -1, 1, 2, 0, and then determinant of matrix A, and we get a result of 1. So we're pretty happy. Yeah. Now, in the next one, you can kind of see that we're sort of in it here, because that's a 5 by 5 square matrix. Right? So if you don't pick and choose carefully what row to work across, then you'll pay a hefty price. In this case, it makes the most sense to work across the last row because there's only one non-zero entry in that row, right? So this is row 5, column 4. All right, that's an important thing to keep in mind, because if you think about the expansion, the cofactor expansion, it's always -1 raised to the sum of the row position and the column position multiplied by the entry at that location multiplied by, and this is where we earn our keep here. Here I'm actually going to do the crossing out because none of the other values are relevant in the row or column. So I'll be left with a matrix that has all of these entries in it. Right? So it's going to simplify down to a 4 by 4. It's like, oh, simplified down, huh? Well, hell of a simplification, but it's still a little bit nicer than what it was. All right, but we're still going to kind of follow the same framework here, right? Because again, we don't want to make this any more complicated than it needs to be. First off, -1 to the 9th power, -1 to an odd power is going to be -1 times the -2 is going to be a. Oh, that was looking good either way. It's going to be a +2. So I'll just kind of hold that thought. But if I'm going to simplify this further, I'm not at a point where I have a 2 by 2 square matrix. So I would want to work across row 3 here because that's the only row that has a single non-zero entry. All right. So we're going to create a second level to this, but it is what it is. So that +1, so I'll circle it here. I'll draw a little arrow. I'll draw a better arrow. That's row 3, column 3. All right. So I'm going to be looking at -1. I don't even think I could do that again if I tried. That's something. How the hell did I do that? That looks so cool. It's just I think it just kind of skipped when I. All right, well, that's insane. If that was a feature built in, that would be like pretty awesome. Yeah, no, I have no idea. So 3 + 3 times the 1 times, and again, a little bit of writing here, and by a little I mean a lot. If I can get a straight line segment, son of a gun heck. All right. So I'm crossing out the rows and columns, or the row and column that contains the 1. And I'll be left with a 3 -7, -6, 0, 2, 3, 0, 0, -1. All right. Now, at this point, it's sort of robbing Peter to pay Paul here. That's completely the wrong analogy, but I didn't know what else to say in the moment, so I just said the first thing that came to mind. It's kind of cool in that this result is going to be, I did it again. This result is going to be a 1. And actually, I just wonder, yeah, you know what, I'll take it as a typo. Swap number 4 and 5. Because I'm about to use the theorem, the triangular matrix theorem that's in number 5 to finish up number 4. So, all right, because what we have now, after simplifying it, using the cofactor expansion, we now have an upper triangular matrix. And we learned last time that if you want to find a determinant of an upper triangular matrix, all you have to do is multiply down the main diagonal. All right. So in this case, we would be looking at a -6. So our determinant, the determinant of A, is going to be 2 times 1 times -6, which is going to be a -12. All right. Now, wouldn't want to do all this work without checking it. So, new matrix, 5 by 5. In the grand scheme of things, checking your work by having to type in all these values, not too bad. The alternative is not knowing that you did it right. If time's a factor, then of course, skip it. I'll put that back in a second. I just couldn't see the numbers. But when I teach linear algebra, I tell my students all the time that sometimes I don't even check it. Because if I make a mistake checking my work, then oftentimes, especially when it comes to some of the computational skills associated with linear algebra, I spend a whole ton of time trying to find a mistake that isn't there, all because I typed the data values in incorrectly into a calculator. And there's nothing more frustrating than that. And I tell my students in linear algebra that all the time, every semester, that on the first unit test, there's always a student who does exactly that. They do the problem. It takes a whole page to do the problem out by hand. They check their work in the calculator. It shows a discrepancy. Then they spend the next hour and a half trying to find the mistake on that page, looking for something that isn't there because they typed it into the calculator wrong. And at the end of the 2.5, 3 hours, they finally raise their hand and say, hey, listen, I know you probably can't answer this, but can you just look at this? I can't find my mistake. And I'll look at it and be like, you didn't make a mistake. It's all right. You're like, oh, I've been sitting here for the last hour and a half and I'm the student you've been talking about. There's always one. So all that buildup was just in case I got that answer wrong, but I didn't. So I'm happy. But you got a story out of it, so it doesn't matter. Right? So determinant, -12, and there you go. All right. So we learn this technique, these techniques, in order to be able to handle the Jacobian. All right. That was the main focus of last class. After we went over some of the older volume problems, but we're going to continue with that today, and then we'll talk about surface area, and then that'll be pretty much it for the course. All right, so we are in the end game. If it was the end game, it would be like another 3-hour movie. So just a little rock, paper, scissors joke for you. So anyway, this question asked us to find, well, it didn't ask us to find anything. I made it so that it asked us to find the determinant of the Jacobian matrix, right? Which is also known as the Jacobian determinant, or just for short, the Jacobian, all right? So what we learned is that the Jacobian matrix is a matrix that consists of all the first order partials with respect to x, y, z, whatever the next variable is down the line, and so on, all right, for a system of equations. Okay, so that's what our goal is for this question. So what I'm going to do is I'm going to tuck in another page here so I can actually do this work. Okay, it's not going to take a lot of doing, because we have the benefit of being able to use some skills associated with linear algebra, right? But they are function related, so we have that little twist along the way. Let me get rid of some of this highlighting here, at least temporarily, until I snip this. I got to remember to put that 3 back in. I'll remember. Copy. All right, so let me get a new page in here. Assuming my app doesn't want to freeze up on me and then potentially crash. Okay, it didn't crash, which is good. A blank page. Let me just kind of tuck it in over here. I can't remember. I don't think, I know as far as typos are concerned, somebody, it's usually the same rotation of 3 people who submit the typos, so they're racking up like bonus point after bonus point. Good for them, right? But one of the big 3 typo bonus point getters, I guess, got the subscript. The x sub 3 is what it should have been, but I don't know that anybody submitted the typo find the determinant of the Jacobian matrix as that new problem. So if somebody wants that, even if somebody submitted it, obviously I didn't make the change, so I'll take that also. And you know what, this is probably good enough. All right, so this is our Jacobian matrix, and we need to find the determinant of it. All right, so it's really just the same idea, just it's going to have the functions in them. Right? So, and you know, like for better or for worse, you're kind of getting a little bit of a crash course on some linear algebra concepts here. You know, it is what it is. You know, it's not ideal. You know, this is. Honestly, in years past, multivariable calculus and linear algebra would be a co-requisite, you know, but nowadays it's like you really can't mandate, you know, you can't mandate that sort of thing, because, you know, in a school where commuting and, you know, working around people's lives is kind of, well, is definitely the norm. You know, to tell people, you know, like in order to take Calc 3, you also have to take linear. It's not practical. So the best I can do is just kind of give you a little taste of linear algebra if you don't have the background in that area, because I don't want you. I don't want to eliminate the topics because they're important, but I also don't want it to be like, well, sucks to be you. I guess you're just not going to you're not going to be able to understand this. You know, that's not how I operate. Anyway, so it's a determinant. It's not triangular, the matrix, so right, it's close to triangular. If that 5 and -2 weren't there, it would be lower triangular, and then we could just multiply down the diagonal, but not quite. So what I'm going to do is circle this bad boy, because row 1, column 1, row 1, column 1 involves an entry, the only non-zero entry in that row, right? So we're going to use the cofactor expansion to figure out this determinant, all right? So we're looking at -1 to the 1 + 1 power, multiplied by the 1. Then we're tossing the column that it's in, we're tossing the row that it's in, and then what we're left with, damn it. I didn't really want to get into this, but I guess it is what it is. All right, well, one other thing that you'll have to do, it's kind of not ideal to address this on the fly. All right, it is what it is. In order for a determinant to exist, you have to be dealing with a square matrix. So we don't have one here. So what we're going to do is we're going to make it a square matrix, right? And in order to do that, we're going to just throw in another coefficient, right? And we can do that because these are function related, right? So if you kind of go back to what we were dealing with before, this is the determinant with respect to x sub 1. I'm sorry, the Jacobian matrix with respect to x sub 1, x sub 2, x sub 3. But in order for it to work out, and I can't believe I missed this, it would have to also have an x sub 4 in it, right, in order to find the determinant. So what we do is we add on a 0. Let me make that a little teensy tiny, a 0 x sub 4 to each equation. All right. And then, there's going to be a big old mess now. We'll have a column, an additional column that consists of partial y with respect to x sub 4. All right. So we'd have the 4 entries there, 0, 0, 0, 0, right? Because the derivative of 0 with respect to anything is going to be 0. And then if we're taking the derivative with respect to the variable x sub 4, and there is no other instance of an x sub 4 there, then it would all just zap away. If anything, this really shouldn't have been the first problem. And you know what? It's kind of like the app knows when I'm aggravated about something, because then it stops like functioning the way I want it to. You just draw a vertical line, and then just draw the little brackets there. All right. So that's what should have been there. Or at least this, like, this might be the dangerous territory of me being like, let me make up a problem on the fly, and then finding out after the fact that no, stop doing that. Don't ever do that again. All right. So this whole thing is really equal. Just tuck a little equal sign in there. All right. So we would have a 4th column here containing all zeros. But I ought to make some kind of sense. So with that in mind, we'll be able to find the determinant of the Jacobian matrix. But if you were staring at this problem for like an hour trying to figure out what the hell went wrong, then it was on me, and I apologize. All right. So anyway, so 0, 0, 0, 0, and now all better. At least until I find some other way to muck it up. So multiplied by 0, 5, 0, 8 x sub 2, negative 2, 0, 0, sine x sub 1, 0. I'm just going to move these things over a little bit. And the bottom line is you're really just looking for the behavior around a certain point. Now, this is all in terms of a function, so it's all in general terms. And again, it just might have been a really bad example to choose, but we're going to find out in a second. Actually, I could already tell you the whole thing's going to zero out, but at a minimum, it's practice. You know, so we're looking at this given a result of that one. I know what happened. This gives a result of 1. Now, when I break this one down, you know, you just pick your poison. It really doesn't make a difference. Go with the 5 if you want, you know, that top entry. So we'd be looking at, this is a row 1, column 2. So you'd be looking at negative 1 to the 1 plus 2 times the 5 times, and you'll see at this point that it's all going to zero out. But like I said, it's practice with a skill. So at a minimum, it's something. All right, so this whole thing zeroes out. And so therefore, the Jacobian is equal to 0. All right, and without getting into what this graph actually looks like, you know, because it's a vector valued function in 4 dimensions, if you know that the Jacobian is just telling you basically, you know, a multivariable rate of change surrounding a particular point in space, this is telling us that there's a value of 0, so a rate of change of 0, right? So it's constant in some capacity, right? So it's a nice outcome. It's not, you know, once you get down to it, it's not the most challenging kind of problem in terms of finding the determinant, but you know, you kind of did all the work to get to this point, so maybe it is a good problem because it's the reward at the finish line to being able, you know, you come up with your Jacobian matrix, you did all the work to get there, and then in the home stretch, you're like, oh, okay, so kind of nice, you know. So the next problem, asking for the, again, Jacobian determinant. And this is leading us towards the volume of an ellipsoid. So we're going somewhere with this, and I'll just underline or get rid of all those markings there. Find a Jacobian determinant of this vector valued function, right? So, or this set of vector valued functions, or at least it would be when we clean it up. It's this one at least is 3 by 3, so that's a win. That's something. So notation wise, it could always be a little iffy. but we're looking for, and you know what? It's in 3 dimensions. So what we can do here, just to make our lives a little bit easier, and I don't know, maybe this doesn't bother you, but the subscripts, if it's anything less than 4 dimensions, then you probably want to just go with X, Y's, and Z's, just for your own sanity. I might be the only one that actually struggles with that, but it is an issue. All right, so Y is equal to, all right, so we have, well, this is actually going to be our function. I'm just debating. I'm going back and forth on this. Does it make a difference? You know what? I'm just going to leave it as is. So we're looking for the partial y with respect to x1, partial y1 with respect to x1, partial y2 with respect to x2, partial y, no, still y1, sorry. With respect to x3. And then just to save myself from myself, I'm going to do some copy pasting here. The 1s become 2s for the y's. It's kind of like pick your battles, I guess. So anyway, I'm going to take the derivative of this with respect to, get out of here, with respect to x of 1, then x of 2, then x of 3. The beauty of at least the first part of this, sorry, I just got to check something. I just had a moment there where I was like, I didn't copy paste the same example, did I? And it's close, but it's not exactly the same. All right, so with respect to x of 1, we're going to get a 0, because there's no x of 1 in there. And I'm just going right for the determinant notation. So I'm not making it a Jacobian matrix. I'm just going with the absolute values on it because we're going to have to do that anyway. So I'm just kind of saving myself a step. All right. One less thing to forget. You know, with respect to x of 2, it's just going to be a 5. I might have to move some things around for spacing, but we'll see. With respect to x of 3, there is no x of 3, so a 0. Now the second one, that's where things get a little goofy. So for organization, I'm just going to highlight it so I keep looking at the same thing. All right. With respect to x of 1, that's just a 4 to start. I'm sorry, 8x of 1. Is that what you're going to say?
Yeah, so on the third column, why is it dy1 over dyx2?
Because I accidentally wrote the x of 2 and then I copy pasted it 3 times. Thank you.
I thought it was had something. I was confused.
Some fancy rule. Yeah. Nope, just me being me. Thank you. So 8x of 1 is what it ought to have been for the first entry in the second line. When we do it with respect to x of 2, the 4x of 1 squared goes away. So then we're looking at -2 cosine. All right, so let's see if I can get it in there. The -2 cosine x of 2, x of 3. But we're doing this with respect to x sub 2. So we're multiplying it by the coefficient of x sub 2, which is x sub 3. I'm just going to tuck that in there. We'll see if I have enough room for the last entry. I think I will. If not, save, save. Schmidge it over a little bit preemptively. These are going to have to move over now. This is all right. And then for the last one, there's no x sub 3 in the 4x sub 1 squared, so disregard that. So this is going to be the same thing, just multiplied by the derivative of x sub 2, x sub 3 with respect to x sub 3, which means that it's going to be negative 2 x sub 2, and then everything else is the same. Like a glove. Yeah, it's a little too tight. I probably don't need my bars to be this long. All right. So then the last entry, or last set of entries, with respect to x sub 1, x sub 2, x sub 3 again, but this time we're looking at this one. So with respect to x sub 1, there is no x sub 1 in there, so 0. With respect to x sub 2, so the x sub 2 goes to 1, so it becomes x sub 3. And with respect to x sub 3, the x sub 3 goes to 1, so x sub 2. All right. So now we just have to find the determinant. Just little things, you know? So it looks like row 1 is the winner. Let me get red there. I'm going to go with that row. That's row 1, column 2. So we're looking at the determinant being negative 1 to the 1 plus 2 multiplied by the entry at that location multiplied by the matrix that remains after I eliminate the row and column that contains that 5. All right. So the determinant of that matrix would be the determinant of 8x sub 1, negative 2, x sub 2, cosine x sub 2, x sub 3. Kind of never been happier to see a 0 as an entry. We have the x sub 2. So then we can apply our diagonal down, diagonal up here. So we know that this one, do it again, that's like 5 for 5. Negative 1 to the third power is negative 1. So that's going to give me a negative 5. The diagonal down is 8 x sub 1, x sub 2. Diagonal up is 0, so that goes away. So my Jacobian is going to be negative 40 x sub 1, x sub 2. Phew, Jackman.
Professor?
Yeah.
If I convert the x1 and 3 into xyz, and I get an answer, I get the same answer, except instead of x1 and 2, it's x and y. Is that okay?
Beautiful. Okay. Yeah, not a problem. That's perfect. In fact, I had toyed with doing that initially, except I had a big fear that I was going to somehow screw it up. So I was like, you know what? Let me stay with it as is. But yeah, if you can keep it straight, then totally. All right, so then the last one in this little mini topic is we want to find a rule that gives the volume of an ellipsoid, right? And you know, you can Google rules. Rules are galore. You know, you find rules everywhere. Right? We want to use the techniques that we just learned about to do that. Right? So we have the general standard, you know, the general standard form. There's not really a contradiction, but it still kind of feels that way. We have the standard form for an ellipse, x squared over a squared, you know, centered at the origin. X squared over a squared plus y squared over b squared equal plus z squared over c squared is equal to 1. Right? Now, we can actually use these techniques to sort of get us going in that direction, right? So, or in the right direction, I should say. So the first thing we're going to do is kind of decompose this into vector value functions so that we can kind of apply what we were just learning. All right. So we're looking at an alternate form. We could say x squared over a squared is really the same as x over a as a quantity squared plus y over b as a quantity squared plus z over c also quantity squared equal to a 1. The benefit of writing it this way is that we can create a substitution that would allow us to swap out the x over a, the y over b, and the z over c for something simpler. All right. So we would let u equal x over a. We would let v equal y over b. And we would let w equal z over c. Now, there is an orthogonal relationship between these three vectors, u, v, and w. But what we would actually do is we would really just kind of write our function in terms of those vectors, because I would be looking at this and saying, if I take u, you know, just the definition of some vector u and find the cross product with that, between that vector and v, I would get vector w as a result. You know, in the case of an ellipsoid, that becomes even more important, because if you think about the internal structure of an ellipse, you know, so ellipse in 2 dimensions, they're perpendicular to one another, the major and minor axes. All an ellipsoid is an ellipse with height, so that third axis is shooting upward from that perpendicular set of axes. So the x and y axis, for example, followed by the z-axis would make the major, minor, and the z-axis for an ellipsoid. Right? So we have that kind of ongoing flavor going on. So what I can say here is that, you know, just to kind of keep it in terms of the appropriate variables, or to make it even, just make it simpler if we want, I can let u equal x over a and so on, but I can also solve this for x is equal to au, y is equal to bv, and z is equal to cw. All right. The benefit of doing that is I now have a function that I can call f, to be very creative about it, f of u. Well, it's really f of x, y, z, which in turn becomes f of u, v, w, which gives us the vector valued function au, bv, cw. All right. So we're applying or we will be anyway, we'll be applying our knowledge of the Jacobian to be able to find the behavior around some arbitrary point in space based off of this vector valued function, right? Because the vector valued function here defines, based off the parameters that we established, it defines the ellipsoid. So I'm just got to write stuff again, but I have to find the partial with respect to u, v, and w for each component. All right. So this really, and actually, I don't want to jump the gun here. This could be thought of as three separate vector valued functions, AU 0, 0, zero, BV 0. Let me just get this out of here for a second. I'm just going to tuck it up there. Zero, zero, CW. Yeah. So we're decomposing it into three separate vector valued functions, specifically the cases along the X, Y, or the U, V, and W vectors, right? So this would really become F of U, F of V, and F of W. All right, so I'd be looking to find F of U, V, and W for each one of these functions. All right, so I'm kind of looking at this as an umbrella kind of idea. Instead of writing it out a bunch of times, I'm just saying we're finding this for each of those functions. All right, so we're going to be looking at a 3 by 3, but it's going to be pretty easy to compute in a lot of different ways. Let me just highlight. So the derivative with respect to u would be a 0, 0. With respect to, so it would be the derivative with respect to a, can't even talk. The derivative with respect to u for the first entry would be a. Everything else would be zeros because the derivative of a constant, no matter what the variable differentiation is going to be 0. All right. In the second case, zeros go to 0. The derivative of BV with respect to V is going to be B. In the last case, zeros go to 0. The derivative of CW with respect to W is going to be equal to C. All right. And so from this, we get a determinant of ABC. All right. So I'm just going to kind of move some things over here. right. So it kind of begs the question, all right, we got that ABC. What do we do with that? You know, so we can actually do a lot of things. So we now have a multiplier that'll help us to find the volume of an ellipse, right? Or sorry, an ellipsoid. So let me pull up GeoGebra. Oh, you know what? Oh no, I think it reset me anyway. So there's a plane. Hate the plane. We have this function x squared divided by 1 plus y squared divided by 4 plus z squared divided by 9 equals 1. All right, so that's my ellipsoid. Volume of my solid, if I can get to parentheses here. Always the issue, right? Q1. Well, that's what my solid is. Now, you know what? Give me a hard time. All right, how about this? Volume of ellipsoid. So the ellipsoid formula is 4/3 pi ABC. All right, so the ABC has meaning to it. So basically what I was hoping to show you, if GeoGebra functioned properly, was that the product of A, B, and C, in this case 1, 2, and 3, 6, would have given us 6 multiplied by 4/3 pi. All right, and it would have resulted in an 8 pi. But unfortunately, that didn't get the job done because GeoGebra's being obnoxious right now. Or maybe I'm just misremembering how to type it in, but I'm not 100% sure that's what happened. All right, so, but you know, let me just move this over here and get rid of that. All right, so what we would want to do is use spherical coordinates to help us determine the volume here. But the good thing is, if something is spherical in nature, whether it's oblate or just an ordinary sphere, your basis for that computation is always going to be the rho squared sine of phi, then your d rho d phi d theta. All right. So what we're looking at really is taking a unit sphere, so 0 to 1, 0 to pi, so 1 unit out from center, working our way down from 0 all the way down to pi for phi, and then spinning it around to give you a sphere. All right, so that's 0 to 2 pi. This part of it is a unit sphere. If you multiply that by the multiplier associated with the Jacobian for the vector valued function for an ellipsoid, then what you would end up getting would be the volume of that ellipsoid. All right. So we could carry out the process, but it's really not overwhelming, you know, especially since the computation is really just, you know, it's kind of asked and answered, right? We've done this a bunch of times, right? So, but, you know, I might as well do it because we haven't touched on, or we haven't gone over spherical stuff tonight, so might as well. But it's not really overwhelming, like I said. So 1/3 rho cubed sine of phi over the interval of 0 to 1. All right, so you pop in a 1 for the rho, and so we're looking at 1/3 sine of phi. That's being integrated over the interval of 0 to pi. The phi, the antiderivative of sine is negative cosine, so negative 1/3 cosine of phi over the interval of 0 to pi. So we're looking at 1/3 cosine of pi minus, for quality, minus negative 1/3 cosine of 0. All right, cosine of pi is equal to negative 1, so a negative 1/3 times negative 1 is obviously a positive 1/3. Cosine of 0 is 1. 1/3 plus 1/3 is 2/3. So then we integrate that over the interval of 0 to 2 pi. You know, you can save yourself the time, because if you remember one of the old school rules for taking the antiderivative of a constant function, you just multiply the integrand by the difference between the bounds, and you got it. In this case, it would be 4 pi over 3. So I'm taking that and multiplying it by ABC. All right. So as long as you can identify what the A, B, and C values are, you have your volume. All right. So the A, B, and C values in this case are 1 times 2 times 3, which is a 6. So 6 times the 4 pi over 3 is going to be 8 pi even, and that would be your volume of the ellipsoid. Right. So not as smooth as I would have liked it, but you know, we kind of got there. So 8 pi. You know, so the idea is for you to get a little bit of a taste of what's happening with, you know, vector spaces. You know, it's kind of weird because, you know, the introduction was sort of ham-handed in the sense that we went from volumes to, all right, let's talk about determinants and then slap it all together. But it was for a purpose, and it's also so we can get some vector calculus involved in this. So that's the idea there. So the last thing I wanted to talk about in the course is surface area. It's actually a pretty straightforward concept, although the next page will make it seem like it's not. I did change a couple of pages on the back end, right? Actually, I think it was the last 2 pages, only because the problems that I had there, they relied on some other prior knowledge that just isn't there, you know, because they were basically copy paste jobs from some of the volume questions that we did, but you had to kind of learn a little alternative approaches to stuff in order to be able to handle those. So I changed those up just to make it a little bit more seamless. But anyway, the surface area idea, and it's kind of nice that it's all coming back to our studies of vector calculus. Really just kind of involves a very familiar looking formula. And I included the derivation of it because I didn't, you know, at the end of the course, and I got to say, in all honesty, at the end of Calc 3, the number of times that I've taught it, I've never had enough time to go through too many derivations at the end of the course. You know, what we just did with the volume formula is pretty much the extent of it. Volume of an ellipsoid. It's just the best laid plans. When you get to the end of a semester, it's like, all right, we're in crunch time. So yeah, as much as I want to do proofs, there just isn't enough time. So what we're looking at here, and it's very, I'm just going to do a little hand waving here because it's very detailed here. What we're looking at is a little teensy tiny little smidge of area contained within the surface of a surface. You know, the area of the outer boundary of a surface. What we're looking for is the integration of all of those little smidges of area in every direction, so omnidirectional. But the idea being that if we could find that single area, or at least an expression representing that single area, then we can propagate that out in all directions and get what we needed. All right. So the big question becomes, well, how do you do that? Well, you could define it in terms of a plane, you know. So we're looking for a parallelogram, a teensy tiny parallelogram that is the projection of the XY plane up onto the surface. So if we think in terms of the volume, we're taking the volume that's contained between the surface and the XY plane. And in effect, what we're doing is we're just kind of projecting upward as if you had like, you know, you're kind of in a biodome or something like that, and you have a flashlight and you're on the floor of the surface, you know, the ground level, and you're shining the light up onto the ceiling, you know, kind of like a planetarium or something like that. And, you know, that little bit of light that is illuminated on the roof or on the ceiling, that would constitute the little bit of area that we were looking for, but it's projected upward from the XY plane. All right. Now, it's also possible that you're not looking for the surface area with the baseline being the XY plane. Sometimes it's some, you know, wonkily oriented plane. And so we define, using our plane function, that the equation of that parallelogram, right? And so, or at least the vectors that make up that parallelogram. And then using our knowledge of the cross product, we can come up with the area, because the magnitude of the cross product gives you the area of the parallelogram. And that's what all of this stuff is detailing for us. All right. So that's a mouthful, but it all boils down to this formula, because if we restrict the size of the parallelogram to as small as it could be, then what we would get is an instantaneous area, quote unquote. And so if we take the sum total of all those instantaneous areas in every direction, then what we would get is the total of the surface area. All right. So what this formula is telling us is something that's very similar to what you've seen in the past. You know, you're taking your partial with respect to x, squaring that, your partial with respect to y, squaring that, adding 1 to it, taking the square root, and then bounding it using a double integral over some region, some unknown region, you know, stipulated in the problem, and then integrating that with respect to, you know, whatever the change is, dx dy, so horizontal vertical change, giving you that corresponding area. All right. So all of this details that. There's a lot going on here, but it boils down to that good-looking formula, which is Pythagorean in nature. But I'll take you through a few examples, and you'll see what the story is. All right. Determine the surface area of the portion of 2x plus 3y plus 6z is equal to 9 in the first octant. All right, so we have some characteristics that we can kind of rely upon here. And the first thing that we want to keep in mind is that when we're looking at an octant, that there are some bounds associated with that, and that's a good thing. All right. So because anytime we have bounds, especially if they're rectangular in nature, that's going to make our lives a lot easier. All right. So in the first octant, we know a few things. We know that x is greater than 0, or greater than or equal to 0. we know that y is greater than or equal to 0, and we know that z is greater than or equal to 0. Right? Which is great. Right? So we have some nice restrictions that we can work off. Right? If we didn't have that, then we'd be staring at this problem for a while. Right? So then next up would be setting up our relationship or our relation using the formula. Right? But in order to use the formula, I need the partials. Now, we're not always going to want to solve an equation for z in terms of x and y, but in this case, it's not too bad. Right? So I'm looking at 6z is equal to 9 minus 2x minus 3y. Divide out the 6z. We're looking at z equal to, if we divide by 6, we're looking at the 3 over 2 minus 1/3 x minus 1/2 y. Very often your partials will be constant. I'm not going to guarantee that's always going to happen, but it happens pretty frequently. So if we take the derivative, the partial with respect to x, we're looking at a negative 1/3 or equality 1. Fix that. Partial with respect to y, negative 1/2. Yeah. So then the big question would be, all right, well, I got that. Now, when I set up my integral, what are my bounds and what is the most appropriate way to integrate? Right? That's kind of, I don't want to say this is the culmination of all we've been working on, but it's a pretty solid application, because if you don't really recognize when it's appropriate to go with rectangular coordinates versus cylindrical versus spherical, then pessimistically, half the battle is already lost, you know? So we're looking at negative 1/3 squared plus negative 1/2 squared. I don't know why I reduced the length of the radical, because I actually need a little bit more. Plus 1. So at this point, we want to kind of make a decision based off of the integrand that we have here. Is it most appropriate to work in terms of rectangular coordinates versus polar coordinates, or cylindrical coordinates or spherical coordinates? Right. So what I'm going to do is take note of my bounds here. First off, they're constant bounds. If I'm looking just as the floor function, you know, the xy plane, I'm looking at rectangular coordinates, which is great. I'm sorry, not rectangular coordinates, constant bounds, which means that it lends itself to rectangular coordinates. But if I also know that the floor is going to be when z is equal to 0, then what I can do is I can set this plane equal to 0. I'm sorry, not set it equal to 0. Replace the z with 0. Depending on the form that you're in, you might replace set it equal to 0. But 2x plus 3y plus 6 times 0 is equal to 9. So we're going to find the function that exists in the xy plane, specifically 2x plus 3y is equal to 9. So 2x plus 3y equal to 9. All right. That's not circular. All right. So if it were circular, then I would be thinking cylindrical. I would be thinking spherical. It's not circular. All right. So I don't want any of those. All right. What I'll do here, snip this bad boy. Let me get some intercepts here. I don't think I need the function. I already wrote it. All right. So if I want to bound this function, I'm sorry, bound this integral, I could do it a couple of ways. I have an equation that I can easily solve for y in terms of x. right? So, you know, just subtract a 2x and divide by a 3. So that's what this guy would be. So y would be equal to 9 minus 2x over 3. You can simplify it if you want. There's really no need to, though. Right? So in terms of y, I can bound this between y equals 0. Let me just draw y equals 0. All right. I can bound it between y equals 0 and y equals 9 minus 2x over 3. All right, which would tell me that my first iteration of integration here should be with respect to y, so dy. All right. Now, just remember from last time when we talked about this, what I was saying is you have the bounding occurring based off of horizontal lines propagating upward from y equals 0 to our function. So what that looks like is something along the lines of like this. Yeah, this guy, this guy, this guy. We capped it on the right-hand side. Really, we capped it on the high side, but it's also serving as capping it on the right-hand side as well. Only up to, up to the function. So all of this out to negative infinity would be captured within that integral, right? So if I integrated if I just integrated this, I would get a function with respect to x as a result, a variable function, and that would tell me that I haven't really captured a finite area, right? I want to capture a finite area, and then in turn make that a volume, and then in order for that to happen, I would need to restrict this so that it's only living in that triangular region in the first quadrant, which given some height would project up to be in the first octave, right? So if I go only from this point to this point here, which has an x value of 4.5, then I've created the appropriate restriction. So it starts off at 0, it gets all these values. And in fact, really, if you think about it, what we're looking at, if I were to do this really truly in an appropriate fashion, when I say that x is going from 0 to 4.5, I'm really saying that I'm accounting for vertical lines, not line segments, but vertical lines going from 0 to 4.5. So if I only restricted with respect to x, then I would only have, I would get a function that is not finite also, or I would get a result that's not finite. Okay? So by restricting in both directions, what I'm creating here is an overlap, kind of like a Venn diagram, that allows me to kind of zero in on the appropriate interval, right? So it's the overlap between these two bounded regions that allows for the capturing of the appropriate base area, right? So, ooh, that kind of made an ellipse. That's sort of cool. That one went a little off vertical, but I'm going to live with it. So that one I can't live with. Oh, now I can't live with the one preview. Well, when I zoom out and shrink it up, I'll be able to live with it. All right. So what that's telling me is that all of this area here is the relevant area, all right, the overlap. All right, but that only happens if I restrict between 0 and the function, the linear function, and then from 0 to 4.5 or 9/2. All right, so dx. All right, so once you do that, then it's a matter of just popping it into the old Desmos calculator there, and it'll spit out the value. But as you know, I'm a big fan of saying, just give me the double integral that'll get the job done, you know. So I was playing around with the calculator because, you know, they're always changing it, and making it better, and I'm always kind of learning new things and getting used to it, moving away from the TI calculator more towards the free stuff. So since we're dealing with a constant function, we could actually do the double integral all in one shot here. Right? So if I were to go from 0 to 4.5, open paren, and then open another integral and go from 0, you know what? We're going to find out if I can do that, because I tried it with constant bounds before and it worked. We're about to find out if we can do it with variable bounds. I didn't really even, you know what? I bet it doesn't work, only because I want it to work so much right now. Right? So, well, we'll find out. We'll learn something together. Third, if anything, it's going to look fancy. Close it up. This part is a dy. Close it up, and a dx, and I already know. I'm such a pessimist. Oh, it gave an answer. Is it the right one? Come on, 63. Oh yeah, that's the right answer. As I was designing a problem for the test today, and I was like, you know what? Kind of tired of putting the integral in separately. You know, doing it the one time and then having to take the result and put it back in. I was like, you know what? Let me just take, after I did the inner integral, I was like, you know what? Let me just put another integral in front of the previous one with the parentheses and see if that worked, and it did. But I didn't try it with variable bounds. I'm just gratified to see that it actually worked. Right? So that's pretty cool. You just got to, we talked about this a couple of classes ago, a bunch of classes ago, as long as you remember the parentheses. After you open your integral, put your bounds in, open a set of parentheses, put your integrand in, close your parentheses, and then your dx, dy, whatever, then you'll be in good shape. So it can handle some types of double integrals. If it gets a little too dicey in terms of the actual process of integration, it might kick you out, but you know, hopefully that doesn't happen. All right. So the second example, determine the surface area of the portion of z equals 13 minus x 4x squared minus 4y squared. So it's a z equation, which is good. We'll do an example in a few minutes that's not z equals, and I'll show you how to handle that. That's above z equals 1, but specifically with the bounds, x is less than or equal to 0, and y is less than or equal to 0. All right. So we're looking, if we're in the xy plane, we're looking in the third quadrant. All right, so that's Q3. Just kind of keep that in mind. Keep it in the back of your head. All right. Fortunately, it's already solved for z in terms of x and y. So when I come up with my first order partial, ready to rock and roll, that's funny, rock and roll, negative 8x, f of f sub y is negative 8y. So I set up my integral here, but you don't want to go too crazy in the early going. You know, you set up your double integral. It's over some region R, right? So it's going to have the square root of your f sub x squared. So that's 64x squared plus your f sub y squared, so 64y squared, plus 1. Integrated with respect to some bounded area, right? Some infinitesimal change in area, right? Now, the big question that we have here is, And it's the same as the big question before. Rectangular, cylindrical, spherical, all right? The presence of the x squared and y squared. We don't have a z squared. If we had x squared, y squared, z squared, I'd be thinking spherical. But because I only have x squared, y squared, I'm thinking cylindrical, all right? So I kind of play that out logically and say, all right, well, if I do that, I got my double integral over the interval of r, intervals related to r. This factor out to 64, you have x squared plus y squared plus 1 dA. That x squared plus y squared is the same as r squared. So that's good news. That cleans up kind of nicely, right? So that's telling me, all right, instead of dx dy, I'm thinking r dr d theta. So then it just comes down to the bounds, all right? So surface area of the portion that's above z equals 1, all right? So we're projecting upward. So again, that flashlight, you know, if you're really close to the ceiling, it's going to paint a bigger area on the ceiling. But if you're really far away, I'm sorry, if you're closer, it's going to paint a smaller area on the ceiling. If you're further away, it's going to paint a larger area. All right, but the point is, where you are in relation to that ceiling is going to impact the amount of area that's contained, all right, in that parallelogram, that arbitrary parallelogram. All right, so what we would want to do is figure out the projection of this surface onto the plane z equals 1. All right, so what we're going to do is solve this equation, z equals 1, the system, sorry, z equals 13 minus 4x squared minus 4y squared. All right, so therefore we're looking at 1 is equal to 13 minus 4x squared minus 4y squared. Add, subtract, do some algebra, you know, the usual business. So 4x squared plus 4y squared, I'm adding those to the left-hand side. I'm subtracting 1 from the left to the right. That gives me a 12. Common factor of 4. So x squared plus y squared is equal to 3. X squared plus y squared is equal to r squared, which means r is equal to the root of 3. All right, now in polar coordinates, you know, we don't need Desmos for this. In polar coordinates, when you're dealing with an r equation, r equals some constant, you're looking at a circle. In this case, a circle with a radius of 3. So we know that we're going out from center only, I think I said 3, radical 3 units. All right. So that gives me my r bounds. That's pretty nice. So I'm looking at, if I can turn my line draw tool off, 0 to root 3. Got my radical. And I'm looking at 64 r squared plus 1. And then we have times r dr d theta. So then I just need my theta bounds. All right, my theta bounds are related to the domain that was given in terms of x and y. X is less than 0, y is less than 0. All right, so if x is less than 0, let me use a little highlighter going on here. If x is less than 0, then I'm looking at this part of it. If y is less than 0, then I'm looking at this part of it. Either way, I should end up in the third quadrant. Now, in terms of theta, that's the interval from pi to 3 pi over 2. And so now we have a nice looking integral here that's going to help us get the job done. Now you can do the double integral here in the calculator, in the Desmos calculator. just the same way we did it before, because the innermost function, or I'm sorry, integrand, is with respect to r. So that's going to give me a clean value, and that clean value is going to be constant as a result because my bounds are constant. And then going from pi to 3 pi over 2 should work out also, right? So I'm going to go for it. Pi to 3 pi over 2. Open it up. 0 to root 3. I'm going to use x's and y's here instead of r's and thetas, just so I don't have to go into the keyboard too often. But I'm going to put the x in front. So x root 64 x squared plus 1. Pull it out. Oh, you know what? I got to open my integrand right here. Open parens for the integrand there. Close it up here. I need a dx. And I close it up. Oh, it closed. I had already closed it up. So I'm going to hit the right arrow, and then I need a dy. All right. So we're looking at roughly 21 and change. All right. So, well, really almost 22. So that's going to give me an approximation. I'll go to 3 significant. 21.928. All right. So really not too terrible. Especially since, you know, I mean, it took me a whole semester to figure this out, although we didn't really get into multiple integration until the last month or so. But yeah, I definitely didn't know this last semester when I taught it, or last year. Would have been nice, although I was still using the TI-84 at that point. So maybe. Anyway, I think we could do one more time-wise. The last one is a little redundant, I would say. I mean, it involves an intersection, but it's not anything too crazy. I want to make sure I do number 3 because it involves an orientation change. Right? You see here that we're dealing with the surface area that's solved for y in terms of x and z. So what I wanted to do is pull up GeoGebra. Get rid of the plane because the plane looks stupid. So I'm going to type in y equals 2x squared plus 2z squared minus 7. Now it doesn't really show you much. So we got to kind of play around with this. I'm going to zoom out. Looks like a kind of a little bullet there, but really what we're looking at is a paraboloid. Right, I'm just trying to get the orientation right here. Yeah, this is more appropriate orientation. Right, so let me just bring that in. Get a good looking image of it here. Oh, you know what? I had it from before. Oh, okay, well, this is a better one anyway. All right, so that's what we're looking at. And you can see that its orientation is different. It's not opening upward or downward. So the big question would be, is there a way that we can make it so that it's opening upward or downward? You know, kind of like a rotation. You know, some sort of transformation that would allow this to take on a different shape. So the same idea for the x squared plus z squared equals 4. That's a cylinder. Let me just turn off this other one, just so we can see the cylinder. What I want to do is change the, like I said, change the perspective. Right. So the idea that we should kind of have in mind is, I wonder, because that you know, on the far side, you know, the pointy end of the paraboloid, that's the negative y-axis. If we could change this, and let's see if it'll let me do it. We could change it so that it looked like that, and change this so that it looked like that. Then we'd be in business. All right, because again, this is my, get the right color. This is the y-axis here. I want that to be the z-axis, right? So there's a couple of ways to handle it. One way would be to actually perform a transformation. And that actually is the best way to handle it, because if we reverse the variables, then we're reversing the axes, right? So like, let's say, for example, I said, switch, you know, in an XY plane, switch X with Y. If you switch X with Y, you're creating a rotation, a reflection over the line Y equals X, but it's basically X, the X-axis becomes the Y-axis, and the Y-axis becomes the X-axis. This is something you kind of gloss over when you're learning all those skills. If you think about it, it makes perfect sense. You're just changing the role in the function. You know, it's kind of like a scatter plot, you know, in statistics. If you're comparing time versus velocity, and then but you change the axes so that the horizontal axis is velocity and the vertical one is time, everything's going to get reversed, but that's because you changed your axes. So what we're going to do is we're going to change our perspective here, and we're going to swap y with z so that the graph is vertically oriented. All right, because the relationship would remain the same. You know, if I change them both, it's still going to have the same relationship with one another. So I take these two graphs, which are horizontally organized, and look at them sideways. It's the same relationship, because I'm looking for the surface area that's inside the cylinder. Whether I'm going out to the left, right, forwards, backwards, up or down, it doesn't make a difference. It's kind of like if I were to say, measure the length of that, you know, measure the length of this remote control, right? And then I tell you to take a ruler and measure it. And then right before, and I said the length, you know, measure the length of the remote control. And then right before you're about to measure it, I say, ha, I gotcha. You'd be like, oh, what do you got? I'll just measure it this way now. It's the same remote control. Whether it's laid out this way or that way or that way, it doesn't make a difference. And hold it in my hand any way I want, right? So that's what we're doing here. And it makes things a lot easier, because now I have z equal to 2x squared plus 2y squared minus 7, and x squared plus y squared is equal to 4. All right. That second one's a little weird, because you look at it and say, well, why did you swap with, I'm sorry, yeah, why did you swap with the z? Well, I swapped 0y squared with the z, you know, whatever the value was in there. So if you look at it this way, you could say x squared plus 0y squared plus z squared is equal to 4. All I did was I swapped that y with that z. And when I make that swap, the z goes away. The z has a coefficient of 0 rather than the y. All right. So we end up with a nice circular equation, x squared plus y squared equals 4, which is a whole lot nicer to work with. This baby lends itself to polar coordinates, right? And this one lends itself to cylindrical coordinates. So I could say f sub x is equal to 4x. F sub y is equal to 4y. Now you may look at it and say, well, why'd you do that? I could have just solved that original equation for z in terms of y. Yeah, you could have. Z would have been 1/2 plus or minus 1/2 the square root of y minus 2x squared plus 7. Best of luck finding the first order partials with respect to x and y for that function, and then plugging it into the formula. No, it's not going to be pretty, so don't do it. Do it this way. So we have the double integral over some unknown region R, square root, partial squared, 16x squared plus 16y squared plus 1, for quality 1, dA. All right, because it's circular in nature, it kind of begs the question to, why would we go rectangular when we can go cylindrical? Last 2 pages of blank. The last 2 pages on the blank notebook are different. Yeah, I mentioned that before. These are the 2 pages that I swapped out earlier. All right. Now, if you want to submit typos, you do it through the Remind app. All right, so just send me a message on Remind saying, and I'll take that as a typo. You just say, mistake. This is what the mistake is. And I give you bonus points. All right. So this is going to boil down to a 16 r squared plus 1. The dA, that's going to become an r dr d theta. And there it is. All right. So now we just need our bounds in terms of r. Now, it looks like we're going all the way around, right? It's circular. And it's not restricted in any capacity. So we know that this is r squared is equal to 4. So r would be equal to 2. So I can establish my r bounds as going from 0 to 2. And you know what? I'll put the r in front. I'm going to do that in Desmos anyway. 16 r squared plus 1 dr d theta. Right. So, and now since it is going all the way around, right, rather than being restricted based off of some stated domain, we're going with an r value of 2, a little off kilter there. We are going from 0 to 2 pi. So we crunch this in our Desmos calculator and we'll have it. All right, so back to the Desmos. Okay, refresh to a whole lot of nothing there, so we'll see. 0 to 2 pi. Open. Another integral. 0 to 2. Open. Integrand. I'm using x's instead of the r's. X root 16 x squared plus 1 Close it up. Dx. Yeah, dx because that's taking on the role of r. Close it up. dy. Let me get this 64 point blah 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 64.467 approximately. I'm sorry, 68.467. Oh, I got 64. And that, as they say, is that. All right, so like I said, I'm just going to toss this problem here because it's a little overkill. You know what? I'll leave it there. I will. I'll post a video solution for it. You know, it's another practice problem, so why not, right? Even though it's overkill, there's no harm in having a solution for it. So, but I don't want to waste your time tonight doing something that's just more. It doesn't really bring anything to the conversation. All right. These are 3 good exemplar problems. If you had an opportunity to look on Blackboard at the breakdown for the test, the first question is going to be a surface area question in 3D, and it's going to be one of these types of questions. All right. So, you know, if you got a pretty decent handle on this, you're going to be in pretty good shape. Now, if you're kind of hedging bets and trying to, you know, use probability to figure things out in your own mind, I did 1 problem where it was in rectangular form and 2 problems where it's in cylindrical form. So hint, I don't know. It's pretty safe bet that you're probably going to be dealing with one that's in cylindrical form, right? So just putting that out there. All right, so that is the course. I'm going to stop the video.